There we go. So we have a midterm win. Next week, Thursday. Oh no! And a lot of you have added this course even after it started. Some of you added it even this week. I'm not sure how Blackboard works. It seems to me when you register for the class, Blackboard ought to automatically put you in the list when I write to you. But for example, last night I wrote to you twice. So did you get 2 emails from me? Who did not? Are you new? Are you checking your BU email? Maybe, maybe not. All right, so I sent you the links to the Echo movie list, as well as the camera over here. So you can go back and review the lectures, and I decided to leave the clicker sessions on since some of you are new and haven't had the benefit of the last week's clickers. All right? And to remind you that the book is optional, but it is a resource. I just made it an option for you. Somebody was asking very purposely, you know, will I be okay if I don't read the book? That's up to you. It depends how well you're understanding what I'm saying, how well you're doing in the clickers. I think the best way is to be here, all right? View the lecture. Now that I have videos of the lectures online, there's an old argument, oh, I don't have to go to class now, I'll just watch it later at the beach. Well, you could, but you need to be here to see it firsthand, real, okay, fully exposed and fully clothed. And later, however you wish to dress, rewatching that video gives you a second imprint, but you need that first imprint in person, right? Where you're in class and you're taking notes and you're hearing things for the first time. All right, taking notes in your computer, not on Facebook, right, guys? All right? Or on paper, getting engaged in class. I've encouraged you already to review every lecture before every lecture. So you're reviewing all the lectures a lot. By the time, right now we're going to our 6th lecture. So my model for you, I bet you didn't do it, was to review all past 5 lectures before you walked in today. If you do that with me, you'll be imprinting. But if you find in reviewing the lecture you still don't understand what basalt is, it's time to go get that book and just turn to that chapter on volcanism and then read only those portions that pertain, and there's a lot of it, to what we're covering in class. Okay? So, do you have to buy the book? No. Do you have to read it? No. Will it help you? It might. That's up to you. It depends how well you're gaining here. And now you have the PowerPoints on Blackboard. You can review those. And you can watch the videos. And there are 2 kinds of videos. I'm interested to see if you like the static echo video that's in the back of the room, or do you like the handheld? Which one helps you better, or are they different? Okay? So let's get out those clickers. We're in a double lecture this week. On Tuesday we talked about basalt volcanism. And today I'm going to scare you. The kind of volcanism that is really dangerous. The kind of volcanism that I might stay a few miles away, Tommy, and watch it, but I wouldn't walk right up to them, as I have with basalt lava. All right, let's get out those clickers. Let's see if this works. This time I tried to have it ready to go. Maybe. All right. Response devices. Yeah, that's us. Auto, that's us. Click on this. Let's go. Da-da-da-da-da-da. Pahoehoe is a Hawaiian term applied to blocky basalt flows. I open the poles. Hey, it works. Wow, I can do it ahead of time. Great. And you can help each other. Which is it? Well, help. Oh, darling, thank you. 4 seconds left. Here you go. Pahoehoe. Poland is closed. 74% of you said false, and the correct answer is false. All right. What is the term for blocky? Way to go. But if you're in that 26%, okay, got some catching up to do. But it's okay. You're in a safe haven here. I just care that you're here. And you're here. All right. All right. Ocean crust is primarily comprised of basalt. Polls are open, fire away. You can be right or wrong, it won't hurt, but make a good guess. And then we'll get the right answer, and then you imprint. Okay? Real exam question. Oh, I got to do the countdown. All right. Now we'll count. And I'll have some coffee. Here we go. 3, 2 seconds. Fire away. 128. Polls are closed. 84% of you said true. Really? And that is true. Basalt. Ocean crust made in mid-ocean ridges and hotspot islands piercing that ocean crust. Made in mid-ocean ridges, moving away, spreading away in symmetrical fashion. Some younger areas where there's hotspots like Hawaii and Bermuda, Fiji Islands, let's go. But that's all basalt. Covered over with a thin veneer of mud, but that's mostly basalt, okay? And next one. Mauna Loa of Hawaii is an example of a cinder cone, composite, shield, lahar, andesite. Whoa. Mauna Loa. Same for Mauna Kea. Which was it? Do you remember? Mauna Loa, Mauna Loa. Let's sing a song. Here we go. Now I got the countdown going. Rolling, rolling. Rolling, rolling, rolling. I know, I can't sing. Okay. And you said Shield Volcano got the best answer. 30% of you said it was a cinder cone. The correct answer is, that is off a bit. It is a shield volcano. Get down here. It looked right on my computer until I go to this expanded part. It's a shield volcano. Shield volcanoes are made exclusively out of basalt lava coming out of fissures. There may be smaller cinder cones. Cinder cones are also made out of basalt, but are, get a picture of it, made out of basalt, but they're all pyroclastic cinders. Cinder cones. Cinder is pyroclastic. The fountain and raining down. Okay? Cinder cones are small. You can run up those hillsides. Shield volcanoes are huge. They just look low angle because you see them from great distances, but they'll be over 13,000 feet high. Mauna Loa and Mauna Kea from the seafloor are actually 30,000 feet high. Isn't that wild? That's a lot of lava. Ooh. Okay, here's another one. Basalts are the most fluid, less viscous, of lava flows. So far, this is a correct statement. Because, why? Why? High T, low silica, high T, high silica, low T, low silica, low T, high silica, none of the above. What am I going to do now? Okay, and the polls are now open. What's the best answer? Real exam questions, I promise you. I will have others. Would I trick you? Now I'll do the countdown. Come on in here. Get that click, click out. Click and clack, click and clack. All right, 4 seconds left. Hurry, hurry, hurry. And whoa, I feel really good about this because 72% of you got it right. All right? Basalts are our highest temperature lava. That makes it more fluid, less viscous. Basalts have the lowest silica. We get the andesite and rhyolite. They have so much silica in them, they get excess silica in the form of quartz. Pure SiO2. They're so silicious. Okay? Basalts do not have quartz. Magmas rise because they, one, form under high pressure, contain water, dissolve gases, have low density, are gravitationally attracted to the moon. Oh, I hate that, none of the above. And now you have it. Fire away. Help each other. Hey, what's the answer? Help. This is the only time you can do that in a communal style. And now we'll start. What do you think? Why do they rise? Magma. Did you do the shower experiment? Magma. Turn that shampoo bottle. Watch that bubble rise. Magma. You need a clear bottle, though. You can see through it. And the pose. Did we done it? Okay. Oh, we're scattered. The correct answer here is number 3, low density. Yes, they're full of volatiles, but the volatiles doesn't help them rise. That sounds like the right answer, doesn't it? All right? But I did emphasize this on Tuesday. That's not what makes them rise, Because when you melt rock in the outer half of the earth, melts are compressive and expansive depending on the pressure. At high pressure, liquids compress and can sink. That's what made the core. When you melted the early earth, deep inside, iron, I melted, and iron was heavy and dense, sunk that made the molten core. Now we've cooled, and so half the core is solid. Okay? Which part of the core is solid, inner or outer? Inner. Ooh, that's very good. Ooh, maybe you don't need that book. All right, good job. Good job. All right. No, but in the outer half of the earth, I melted. After the core was made, the mantle retained the radioactive elements. What are the three? Uranium, thorium, and potassium. Fantastic. All right. They were left in the mantle. So the mantle starts melting. That's the outer half of the earth. Less pressure. And so there, the melts are expansive. As you melt, not melting, but the melt grows. And that gives it low density. Which way do you go now? Up, up. Breaking its way up through earthquakes. Two kinds of earthquakes, tectonic and volcanic. Okay? So we're doing all kinds of review, not just with these questions. Oh my gosh. Ocean island tracts, such as Hawaii and the Emperor Seamount chain, indicate plate motion opposite to the direction of younging of the volcanic islands. There is a younging. Which part of the Hawaiian chain is the youngest? Where Hawaii is, that's right. Okay. Represent the fossilized footprints of prehistoric sea monsters. Result from the migration of the mantle underneath fixed ocean plates. Occur at subduction zones forming volcanic island chains behind a trench. Is that how Hawaii is made? Does Hawaii have a trench? Is Hawaii in the Emperor Seamount chain? Is that an island arc? So what's the best answer? Now I open the polls. Just now. You can fire away. Fire away. Think about it. Real exam questions. All the time. Will you see these next Thursday? Some of them, yes. All of them, no. This one, likely. Polls are open. You're a little bit slower this time. Yeah, you got to study it. Anything? Got it? All right, 4 seconds, 3, 2, come on, the last button, get in there, get in there. All right, and you said, whoa, whoa, by mono, Hawaii is not an island arc. All right, I fell. Mommy. She's a wonderful lady, 93 years old. And she now can watch me on B University. Oh gosh. I better paint them down a bit. The Aleutians, Japan, the Philippines, those are island arcs. Marianas, those are island arcs. We'll do those today. Hawaii is a hot spot. And it makes a track or a chain because the plate is moving over the hot spot. Hot spot comes from the core mantle boundary. It doesn't care that there's plate movement over it. And it burns, 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 burns as the plate moves. Okay? And so the oldest part of the Hawaiian seamount chain, Emperor Seamount chain, is all the way up at the Aleutian Trench going down. This is 76 million years old. So the Hawaiian Islands have been a hot spot for that long. All right. That was a good one. And it's okay. Those of you that are over here, now you got it, right? So we all imprinted. And that's why it's important to be here and have that experience right here. Quit. No, don't save the changes. Save the session data. Yes, that's you. And that's where it goes. Cool. Uh-oh. Woo! All right, here we go. The opposite side. Volcanism. So we make ocean crust out of basalt and then ocean ridges and hotspot islands like Hawaii. Honey, you go in here. What? But the Earth, having spreading in all its ocean basins, the Atlantic, the Indian, The Pacific Ocean, all right, even the Arctic Ocean is spreading. It's got mid-ocean ridges underneath the polar ice cap. But the Earth, is the Earth expanding? No, the Earth is not expanding. All right, so something's got to be taken up. All that spreading and that taken up for all that spreading is, I must do this to people. Oh, he's yelling at me now. I gotta cry. I gotta go cry. I gotta pee. Okay. Okay. So it's taken up as subduction zones. As the ocean crust goes, it goes down. It's altered ocean crust, made out of basalt, altered with seawater. So it's not real pristine, but it finally gets there and it goes down and it melts. It melts, and you melt basalt. So let's look at that. We talked last time about melting the Earth's mantle, green peridotite. You melt the mantle and you make basalt. Look at that pahoy hoy, all right? Isn't that lovely? There's some nice looking pahoy hoy. Come up here later after class and put your hand on some pahoy hoy. So when you melt basalt, you only melt part of it. If I melt it 100%, then I get basalt again. But you only melt part of it because the melt is buoyant. It's going to leave. It's going to leave. It's going to leave. You melt like 20% of it. And so the next rock is not the same. It's called andesite. Here it is. It's gray. It's got different crystals in it. No olivine now. White feldspar, black hornblende. Lovely rock. But it's gray. This is andesite. Now this came from a stream. You can tell it's rounded. So when this is part of geology. When we pick up a rock broken out of a hillside like that, when I broke that out with a hammer, I felt good. These I sampled out of a stream. So I know they came from a stream. They're rounded. But I just don't see the stream. I see the volcano that once was. The volcano, andesite, is only made at subduction zones, where basalt ocean crust goes down. I'm melting. And it's got more silica. So it's a thicker volcanic rock. And it's got more gas in it. More water and more CO2. So it's also more explosive. Now, andesite makes up island arcs. Subduction goes down. Where you subduct, you form a deep sea trench. That trench is over 30,000 feet thick, deep, I mean. We talked about that in the plate tectonic lectures. But because the Earth, when you have a convergence of a plate against another, the intersection, if the Earth were flat, would be linear. But the intersection is 2 to Earth is spherical. And so you get an arcuate chain. An arcuate trench. And behind that trench, about 100 kilometers in, it has to go down, and then I'm starting to melt. I'm melting. Jack. He looked at me as belch. I get all of it. I see everything. And then you melt andesite. So that makes up the beginnings of the island arc, but then even the bottoms of the island arc begin to melt. And now we're starting to melt andesite. And if you melt andesite, and only part of it, you get the most explosive rock there is. Here it is, rhyolite. Look at that, rhyolite. Rhyolite. And if you look at it, this rhyolite's full of fragments. It is an explosion. It is an explosion. Look at all the fragments, pieces. All right? That volcano destroyed itself. So these island arc volcanoes, they grow, they erupt lava, and then they explode themselves. So they alternate between both eruption of lava. Get in here. How was it? Works good every time. Yeah, so that's rhyolite. It flows out. It explodes. Sometimes it makes lava, and lava can be made out of a glassy obsidian. So that's how you make obsidian. All right. Or some of you have this around your bathtubs. This is also like obsidian. It's glass, but it's frothy. It's so frothy, so light, that it floats on water. This is called pumice. How many of you have pumice? Yep, there's one. Come on, let's see. Guys too, yep. You scrape off those calluses, all right? Good for cleaning swimming pools. Stove tops, pumice. It's made here in subduction zones from the melting of andesite. I used to have a fake rock that I could throw at my class with little sponges that look like that. Yeah. And when these things explode, this is what came out of Mount St. Helens. Shotgun pellets of pumice. All right, I retrieved that from Mount St. Helens. And when the explosion happens, the mountain is pulverized into all sizes. And the finest material comes down like dust. We call it volcanic ash. Look at this. Whoa. Blast. Let me do that again. This is volcanic ash from Mount St. Helens, which we'll visit today. Scary. Yeah, there it is. Destruction of a mountain because these volcanic rocks, andesite and rhyolite, be it obsidian or pumice or this one, have so much silica. They're thicker and they're viscous. And when you lose pressure, they're rising, they're rising. What gets the bubbles out of a beer, out of a can of beer? You uncap it. So when they rise, they lose pressure. And all of a sudden the bubbles start coming out. But now it's thick and viscous. So where's it going to go? It'll blow up. You can't get out. It blows up. All right? When crystallized at depth, they slowly crystallize crystals and make granite. So here's how granite's made. It's got quartz, feldspar, mica. All right? So the continuous column, we're making continental crust. And in the plate tectonics lectures, you learn how continents grow. Continents grow in two ways. One, by magma, forming granite at depth and volcanoes at the surface, and also by accretion. All right, the stuff scraping up. Now we'll go back to the PowerPoint. PowerPoint is just an outline of my lecture, rich in visuals. Okay, you're taking notes and listening, and that's what this is for. All right. So most explosive, there they are. And so where subduction happens, it can be where ocean crust subducts beneath ocean crust, and we start melting about 100 kilometers in. Here's the trench. I'm melting, I'm melting. Wherever you're melting the slab, it goes down. We named that Atticite after Attic Island of the Aleutians. We melt here in the slab. We also melt in this wedge where rising water coming out of the subduction zone, the ocean crust is hydrated with seawater. And as it goes down, it gets hot, metamorphosed, and that water rises up into the mantle wedge there, and that starts melting. That also makes andesite. And then the bottom of, and so we make an island arc. It's mostly made out of andesite, and then you melt that too. So where you have multiple sources of melting. Now where your subduction zone is beneath a continent, there it is, that's like the Andes. So the first one we call a Japan-type margin. This is an Andes-type margin, or active continental margin. Right, it shows the same thing, melting of the slab, melting in this wedge, melting of the lower crust that was formed by the andesites, magmas rising, some crystallizing as granite at depth. We've also, look at the fishes, nice drawing, huh? I'm scraping stuff off, so the continent here is growing in two ways. Magma and accretion, and the old geocline that used to be offshore is now folded up. The old geocline, remember what that is? That's the sediments out of the continental shelf before there was subduction. And now they're pushed up high into the mountains. James Hutton recognized in every mountain he went, the highest parts of the mountains, Mount Everest. Mount Everest. You find rocks that came from the ocean floor, pushed up, and they're now intruded by granite, cut by volcanoes. Oh my gosh. Here we go. Now I'm going to scare you a little bit today. These volcanoes are really different. Mount Fujiyama, or Mount Fuji from Japan. So they are made up of both lava and pyroclastic, alternating styles of erosion. Here the lava is shown in dark, dotted, or the pyroclastic debris, intruding, ejecting, destroying itself, rebuilding itself over time in the same place. So subduction, the Pacific Ring of Fire. Look at that. Here's the Kermadec, the Marianas, Japan, Indonesia, the Aleutians, the Cascades. We'll visit all of these. Central and South America, coming all the way down. The collisional zone, the loss of the Tethys Sea, the Mediterranean, we'll visit that. All with subduction and collision. The Atlantic, the only place we find subduction in the Atlantic is in the Caribbean, called the Antilles, and in the South Sandwich Islands. Let's go visit a lot of these places. Subduction, the earth is not expanding, so something's got to be consuming. We start with the Caribbean. Oh, wow. Montserrat, Martinique. Here is Mount Pelée shoved up. The volcanic neck shoved up in 1903, grew 50 feet a day, a volcanic spine, Montserrat's recent eruption. Mount Pelée erupted in a horrific style in 1902. And that's all that was left. And what destroyed it, and I'm going to show you a lot of this today, was a very different kind of eruption. It was not lava. It's called a nuée ardente, or pyroclastic flow. Pyroclastic means broken. It's like the froth of a volcano. The froth, if you boil in a pot of stew, and it froths over the side, there it comes. It comes down the mountainside, this glowing avalanche, so hot, it's 700 degrees, it glows, it's coming down 100 miles an hour, it's in motion of volcanic gas and volcanic ash and rock debris that just obliterates everything in its path. Nuée ardente. Denise, you changed your hair. And this was written. A lot of people died, as you saw. There were 3 survivors that came out. They were underground in a prison, and they stumbled out and were let go. As we approached St. Pierre, we could distinguish the rolling and leaping of red flames that belched from the mountain in huge volumes and gusted to the sky. Enormous clouds of black smoke hung over the volcano. A constant muffled roar. A tremendous explosion. The mountain was blown to pieces. There was no warning. The side of the volcano was ripped out, hurled straight at us like a solid wall of flame. The wave of fire was on us and over us like lightning. It was a hurricane of fire. The fire rolled in mass straight upon St. Pierre. The town vanished before our eyes. The air grew stifling hot, and we were stuck in the middle of it. And wherever the mass of fire struck the sea, and it wasn't fire, it was a glowing nuée ardente. All right, looked like fire, much hotter than fire. The sea was torn in huge whirlpools that careened toward the ocean. The blast of fire lasted only minutes. It shriveled and set fire to everything it touched. Before the volcano burst, the landings of St. Pierre were covered with people. After, not a single living soul was seen. All right? Look at that. Here's one much more recent. The next island, a few islands over, Montserrat, 1996, without sound. What is that? It's a volcanic eruption known as a nuée ardente, or pyroclastic flow. It is broken to rock debris coming out of the volcano. The volcanic froth, look at it moving 70, 80, 90 miles per hour, cutting. It knows no object, okay? Searing, destroying, coming at you, you better run. And then it goes out into the ocean. It goes on top of the ocean. All right? It does not sink. Right on top of the ocean, coming at you. Get that boat going. Where's that motor? I don't know. I can't find the key. Ooh. So let's go travel the world a bit. All right? The Aleutians. I want this. From Redoubt Volcano all the way down to Kiska. Look at all those active volcanoes. Here are the dates when they last erupted in a big way. All right? Redoubt erupted in 1989 last, and a Boeing 747 was caught in the ash plume. This is called a Plinian-style eruption, named after Pliny the Elder. And it sucked in all that volcanic ash, lost 3 out of 4 engines, and started plummeting to the earth. People not in their belts were caught against the ceiling. It was hurling down. You can imagine the panic. All right? And it got the engines restarted just before it got down. Whoa. There's a whole bunch of people found God. And now we come down to the Aleutians. We start approaching Japan. Here are the Kuril Islands. Here is Japan. Look at the trench, arcuate. Look at the trench. It's an arcuate. All right, back sea basin in the back behind where there is some spreading. So it's a very active. Here are the Kuril Islands. There's an eruption. Bird's eye view from a high-flying airplane. Look at that. These volcanoes are like a shotgun. And anything above that is like passing ducks and geese. All right? These volcanoes are so powerful. When they erupt, they have the capacity to blow material into Earth orbit, just almost leaving the field of gravity of our planet. Finally, they get up there, and they get into orbit. So there's a little bit of gravity left. Otherwise, they go all the way to the moon.